All right, our next speaker this morning is Zaara, who's joined us this summer from Harvey College. Zaara's been working this summer with Stella, and today she'll tell us about their project together, understanding the interstellar medium through Voyager 1.
Hi, everyone. Thank you for the introduction, and thank you all for coming to my presentation. I'm really excited to be sharing my work with all of you. So today I'm going to be talking about the interstellar medium, but what is the interstellar medium? The interstellar medium is the region between stars in our galaxy. It's mainly composed of ionized gas that's in total charge and neutral, and also some dust and ice. And all of this comes that are left over from galaxy formation, also gas that's ejected from stars as they evolve. And what's really important about the interstellar medium is that it has different regions of higher and lower density. These higher density regions, as pictured on the picture on the side, which is the Carina Nebula, are the birthplaces of stars. So it's really important for us to understand the density profile of the interstellar medium so that we can better understand stellar evolution in our galaxy. So our question then becomes, how can we map the electron density of the interstellar medium? Luckily, we have two spacecrafts that are in the interstellar medium. So the Voyager spacecrafts were launched in 1977 to do a flyby of all the outer planets, and they sort of just kept going and entered into the interstellar medium beyond the sun's influence. And this is a really important distinction because as our sun moves through the galaxy, it's constantly ejecting charged particles. This is just because it's really hot. And as this moves around our galaxy, this interaction creates a sort of pressure bubble between the stars, between the interstellar medium gas and the charged particles released from our sun, which is called the solar wind. Thankfully, Voyager is far enough away from this interaction, really far away, about 25 billion kilometers away, that it can give us measurements of the interstellar medium independent from our sun's influence. So we're going to be focusing on Voyager 1 because it has a working plasma wave system. The plasma wave system is these two radio antennae right here that give us electric field measurements of the interstellar medium. This is important because they can pick up something called plasma oscillations. What are plasma oscillations? Let's take a step back for a minute. The sun can have these solar events called coronal mass ejections. This is just a huge burst of plasma that travels at about thousands of kilometers an hour. This is a picture of the biggest coronal mass ejection that we've ever observed, which was in 2000. And these can send shock waves through the solar system and into the interstellar medium. The shock waves that it sends are magnetic field waves and cause the electrons in the interstellar medium to oscillate in a very well-defined way called plasma oscillations. This is well-defined for the environmental conditions of the interstellar medium as well, and because it's so well understood from plasma physics, we have a very strong relationship between plasma frequency and the electron density of the medium that this oscillation is happening in. So due to this relationship, we can map out the electron density of the interstellar medium on Voyager's path using the plasma frequency. So we can modify our question to be, how can we find the plasma frequency of these oscillation events in the interstellar medium using this Voyager 1 data? So the raw Voyager data looks like this. It's just a really simple voltage time series graph. But it contains some really important frequencies. The first thing I want to point out is that there are some telemetry errors, which are these spikes. You can see them both on here and also just the spikes here. These are just from signal processing things that when the data is being read back on Earth and being sent to us. Oh, the other thing is the bigger wavelength oscillations are just spacecraft noise that just Voyager makes as it goes through the interstellar medium. We've also got some higher frequency power supply noise. This comes from the radioactive power supply that Voyager has. And the important part that we really care about is approximately 3 kilohertz plasma frequency oscillation. So we chose an oscillation event on June 2nd, 2018 that had a plasma frequency that was away from our power supply. You can see there's like a significant gap between these two lines. And the reason for this was because we wanted to be able to isolate this plasma frequency. Yes, I forgot to mention, on the left, on the right, we have a Fourier spectrum. What a Fourier spectrum is just a way to decompose our signal into its frequency components. This is an important part of what I'm doing in my project, but Fourier decomposition has a couple of issues that I'll get to in a second. So we have this signal that's decomposed, but we really only care about the plasma frequency. So we put it through a couple of filtering methods that I can go into more if people have questions, but we really just isolate the plasma frequency region. Fourier decomposition, as I said, has its limitations. It really has a coarse resolution for both frequency and time. And you can sort of see that here. It's hard to pinpoint exactly where the plasma frequency is in this whole region. So another key aspect of my project is using a more advanced decomposition method called the empirical mode decomposition. The details of this method aren't super important, but the main thing is that we have our signal and it gets broken up into physically relevant components of higher and lower frequency. And this decomposition method doesn't have the same limitations that Fourier decomposition has in both the frequency and time resolution. So here's our main signal, and it's decomposed into our plasma frequency signal and some low frequency noise. So this analysis method was taken from literature in the field, but we wanted to check what restrictions this method has. So we simulated a signal with our main components, the power supply and our plasma frequency and also some noise. So we can just play around with the free parameters. There are a lot of free parameters. And one of the things that we noticed was that Voyager has a really fixed sampling frequency. This is just the rate that it's collecting data in the interstellar medium. When we calculated the plasma frequency for different rows in our data set, with Voyager's sampling frequency for our simulated data, we expected to get this red line plasma frequency of about 3,180 hertz, which is what we'd put into the signal, completely simulated. But when we used Voyager's sampling frequency, all of our data was biased low. It was much lower than what we expected. When we doubled Voyager's sampling frequency, we were able to recover this simulated plasma frequency a lot better. So this could be telling us that something in our analysis method is biasing our data low, specifically Voyager's sampling frequency. Another thing that we noticed was that our analysis introduced some noise into our plasma frequency results. So when I plotted the standard deviation of our noise signal that I simulated, which is on the x-axis, as well as the standard deviation of the plasma frequencies we got back out, which is on the y-axis, we found that even when I put no noise into our signal, so it's just a pure plasma frequency signal, we still got some standard deviation in our plasma frequencies. And this is also important to keep in mind when we look at our actual data results. So these are the results that we actually got for this plasma frequency event, June 2nd, 2018. We found a plasma frequency of about 3,160 hertz, which is within what we expected after our initial measurements, which corresponds to an electron density of about 0.124, around here, 124 cubic centimeters, and which is also what we expect in the interstellar medium. It's about 10 times more dense than very, very diffuse regions of the interstellar medium, but it's consistent with what we expect from warmer, more dense regions. And another thing to point out in this result is that there is a big spread in our data. There's this like band of about 25 hertz. This is something that we didn't expect from our simulation results. It's more noise than we simulated. So we think that it could be telling us something physical about the signal that we're getting from Voyager, and we have yet to explore whether it's statistically significant, something that we want to do in next steps. Some of the other things that we want to do is compute a power spectrum using our electron density map. A power spectrum essentially tells us how electron density fluctuates at different wavelengths. This is important because we can then use this power spectrum to understand how turbulence in the interstellar medium works. People in the literature have done this, and they fit a power law here to the data that Voyager has given us. And they found that at really, really small scales, the Voyager data seems to deviate from this fit. So it doesn't seem to completely fit with a Kolmogorov model of turbulence at all timescales. At really, really small spatial scales, it seems to deviate. So we want to verify this fit, check at really, really small spatial scales what's happening and whether this deviation is just noise or whether it could be telling us something physical about the dissipation scale of turbulence, which is the scale at which energy stops being transferred and starts dissipating into the medium as heat. Thank you for listening. That's a lot of next steps to do. But yeah, here's some conclusions. I'll keep them up there as I take questions.
I think the time period you showed where you calculated the plasma frequency on the real data was like a few hours long, maybe?
A few hours? This one? Milliseconds.
Oh, okay, not even that. So I was gonna, is that like a random point in time, or was something interesting about measuring the plasma frequency at whenever this brought up?
I think this is just the Voyager collects its data in about 48-second periods. And this was one of the periods that matched up with a plasma oscillation event that happened on that day. So most of the data that we get is like snippets of 48 seconds. And yeah.
I thought you could kind of always measure the plasma frequency, so plasma oscillation event, because it's something you can only measure at certain times when the electron density is high.
I think it's just a Voyager limitation of when it's collecting data, because it's not always collecting and returning data, at least from what I understand. But yeah.
Okay, so you find a let's see, electron density that you said is like 10 times higher than kind of the more diffuse regions. And I'm curious how that fits in with kind of the Kolmogorov spectrum plot, because there's this little bump at the smallest scales associated with Voyager, I believe, and if Voyager is in a region with higher than typical electron density, like how does that connect?
This is using data from from a longer time scale. So we just focused on one event to sort of check our data analysis method. But the people who plotted this plot here are using much longer, I think from 2012, and they just have used a lot more data. So the data that they get just spans just a much longer time scale. I'm not completely sure about how my data ties into this. That's something that we're going to start exploring in the next steps. But does that answer your question?
All right, let's thank Zaara again.